Hello and welcome to another entry of invalid video. Another video of invalid entry. It is December the 21st, which means we've done somewhere in the region of 45 videos this month, and it's going really well. And I'm in my Christmas outfit because it's Christmas. Basically today you can see the advent calendars filling up really well. Next year I will not put them behind my head, but we've only got 3 days left of today, and today I believe is this one up here, or it might be the one behind my head. Anyways, new notes. Yesterday we did a music video and it was badly done on the audio, so I'm hoping the audio on this video is much better. But today, also I cheated because I used a microbit, and in microbit you can just say play music or play note and it plays a note for you. So today I thought I would do music from scratch. So I've got this thing here called music from scratch. This is going to be horrendously offensive to all musicians out there, as I am basically using these to learn about things that I don't know a lot about, and I don't know a lot about music. So I have here my trusty crib sheet for the notes to Jinglebells, and we are going to program music from scratch. The end result of this is effectively we might even be able to make jazz, a pure, unadulterated jazz, because everyone knows all you need for jazz is the random number generator. Right, so what we're going to do, obviously for music, you want Numpy. And also we're going to look at the waves as well. So we're going to import matplotlib.pyplot as plot, because I can't remember bother to type that in every time. Right. Basically, what we're going to do is we're going to make waves from scratch, and then we're going to export those into WAV files. So we're actually going to do the generation of the individual notes. The first thing to us is we want to have a sample rate, we want a function that's going to make the wave. This is all based upon a fantastic blog post, which I'll put in the description below. So I've done things slightly different to him, mainly because I don't like the way data scientists compress their loops into single lines. I've expanded them out a little bit to make them a little more obvious what they are. Make wave. So frequency and duration equals 0.2. I'm going to hard code the amplitude. In future I might make it so you can put different amplitudes in. Amplitude being the volume of the wave, the amount of energy you're putting into the individual pulses of air you're going to receive in your ears. I'm going to put that at 4,000. Right, so basically NumPy has some very funky things that allow us to generate entire arrays of data very, very rapidly. So we can do this by x equals np.linspace naught duration and int sample rate times duration. So basically what this is going to do is going to take the sample rate, which I want to put in up here. Sample rate equals 44,100. Now the reason we use this because this is what people do. Now it's interesting, the sample rate basically sets the maximum frequency that you can render when you're creating digital analog signals. That's basically going to create my space, and then go to wave equals the amplitude times np.sin 2 times np.pi, because there's radians in a 2 pi radians in a frequency, times the frequency times the space that we just made, and then we're going to return that wave like that. That function will basically make us a wave. So if I now have a frequency of, let's say, 262, which happens to be C, don't ask why, we're not going into musical theory here. We're not going to a lot of musical theory here, mainly because it's a great insult to people who know musical theory, but there it is, that's it. So a wave is going to be make wave frequency. That has basically now made, if I do len a wave, is going to be that many samples. And it's that many samples because basically the sample rate is that, and I asked for 0.2 seconds, so that is 0.2 of, about a fifth of that size. But each of those values are actually a different value between a negative number and a positive number, which goes into your thing. So what we're going to do very quickly is we're going to plot that, and don't worry about this wave. I'm going to plot the whole wave to begin with. Plut dot x label is time, and plut dot y label is going to be amp, and plut dot show. And as you see there, I've got this wave, and if you count the number of peaks, you should have 1/5 of whatever that fraction is. Now what you can actually do here is, I don't want to plot the entire wave. What I want to do is I want to plot just the number, so I can basically do 44,100 over frequency to get that number to come out nicely. So it's just going to show one cycle, and that didn't work because I taught it frequency, not freak. There you go. That's just one part of the frequency. You notice it goes from 0 to 1. So it may be a bit hard to read on your screen because I've got the nice black background here. That's one sine wave going on. If I change the frequency, it just makes this scale change. It doesn't really change the picture very much because it's always going to be on sine wave. What's interesting here though is that this frequency is mapped to the sample rate. So if I increase this massively, if I put it at 22,000, you begin to see it still renders quite nicely. There's a number of points in this is still quite good. If I put it to 22,000, oh, didn't actually run it. You start getting very dodgy numbers come out. If I put it to 2,600, you begin to see the artifacts begin to come in. It's no longer a nice smooth curve. It is a line-to-line point because that's actually what we're doing. And this is now 14 milliseconds across rather than it being 140 milliseconds across. So you've got to be aware that basically your sample rate defines the maximum frequency that you can basically represent in this scale. So let's put that back down to 226, which is perfectly good for human hearing. It's interesting this because I have this chart here that shows me different scales of hearing from Wikipedia. And humans can basically hear between something like 30-ish hertz up to around 20 kilohertz. I don't think I can hear 20 kilohertz. I think my hearing, so you get older, you lose hearing. And I think you can damage your ears by music, and there's other reasons. You think you can train your ears to hear better, but I don't have that high-end frequencies. But it's quite interesting here that whales seem to only start at 1 kilohertz. Because I thought whales could hear quite low things, but you know. Also, they doused this. They found out this range by talking to the animals. They get a goldfish in a bowl and they say, "Can you hear that?" And the goldfish goes, "Hear what? I don't remember." That's a joke about goldfish memory. Right. Jokes are better if they have to be explained. Right, so we've basically got a sound here, we've got a frequency, we've got a whole bunch of samples in an array. The array is quite long, it's going to be 8,000 samples long or whatever. So we're going to write it out. So handily, from scipy.io, import WAV file. Yep, WAV file. That looks weird. From scipy.io. I just want to check that I'm on the right kernel because I suspect I'm not. And restart my kernel, just run through everything. SciPy, this doesn't like SciPy, there we go. There we go, it's important. Well, we now have the ability to wav file.write out.wav. I want to write the sample rate. Make sure this sample rate matches the sample rate you're actually using, otherwise you're going to have weird things. Wav .as type and np.int16. If you get that wrong, basically it's just changing the accuracy of your numbers. Get that wrong, you won't have a very good WAV file. I'm sure people who are experts in WAV files will do that. Anyway, up here we now have an out wave. That was it. Hopefully you all heard that. I'm just going to do that again whilst actually looking at the output correctly to make sure it did go. Yeah, right. That was a C. Believe it or not, that really was a C. Right, so moving on. What we want to do now is actually turn this into sound. So what we can do is we can do a song is equal to an array. And what we're going to do here is we're going to do an array of objects here. Musical notation, I can't read music, so we're going to program that stuff. Just invent thousands of years of music theory in... well, just a few seconds. Right, so we're going to have something like this, which tells me the frequency, and then basically what I'm going to do is I'm going to times one of these by 2. I'm going to make one of these divide by 2. I'm also going to make this one shorter, and then this one's going to be times 2 again. So we're just going to get a whole bunch of sound. This one's going to be slightly longer. Right, there we go. There we go. That's my song defined as a block of data. There's no rests in between. So what we're going to do now is go waves is equal to an array. For note in song, we're going to do waves.append make wave, and then do note frequency note period like that, and then that will give me an array of arrays. So this will be a two-dimensional array. Pretty weird. Each sub-array will be a different length because some of these are longer than others. I'm going to output equals np.concatenate waves. I use the NumPy concatenation rather than doing the array concatenation because I've got NumPy open and the np one is faster. So if I then that, you basically get 40. Oh, I've got a second. Let's just add that up. 0.2, 0.4, 0.5, 0.8. 1 second. How about that? 1 second worth of output. Exactly 44 kilohertz. That was completely accidental. Did not know it was going to happen. If we actually want to plot this, I'm just going to grab my code from here and change that there to just output. What we should see here is that there is some very distinctive wave changes here. You can see the slow one in the middle, and this one seems to be faster. It's going up and down faster than this one. It's quite hard to see because the chart's so small, but there is very distinctive different notes going there. And then what we do is we write that out as a song. So we can do song.wav and we can do output.wav as that. So write that file out, and already we have the file there. There you go. There we have a song. Fantastic. How are we doing on time? We've already got music. I mean, basically, we've got jazz coming out already, if I'm honest with you. We're here to make Christmas songs. It's also worth realizing these should really be in functions, because if they're in functions, then when I come out the function, anything I've got open, like these wave arrays, would get garbage collected rather than be open in memory. I could do del's, deletes, and manually, but at the moment, this Jupyter notebook, we're doing it from scratch. If you have problems doing this, you make a stupidly long song, just close your kernel, quit the kernel, hard restart the kernel, because you may just have massive arrays. If I do sys.get size of output there, that's 350k, so it's a third of a meg. That'll be read in 4 votes. So just be aware you can quite easily, if you do a loop and say I want to just loop this 10 times or whatever, you can very easily use up a whole lot of memory. And especially if you've been copying it twice. So here I've got my wave files. You can avoid Python taking a memory copy by writing the code slightly differently. So to write the code differently, you would write it as one line. You wouldn't do the 4. You would actually do something along the lines of, if I just take those 3 lines there, you would actually do something along the lines of np.concatenate this is me thinking really hard. I don't like these for loops. Basically, I'm actually going to look one up very quickly because it's worth looking it up. Yeah, okay. You would do something like... actually, no, you would have something to make it. But you could do something like... You could get rid of this slightly, but you'd still end up with a loop. You still end up with a device. Ignore that. Ignore that. We're moving on. Right. So what we want to do now is we actually want to make individual waves of sound. And I'm just going to hit a thumbs up somewhere. Right. There we go. We actually want to make individual notes of sound, and we want to crack on and do this back to back. But we want the notes to be the standard Western notes. So I'm going to make this thing called def generate notes. And this is going to generate me my note array. So basically what I want is I want there to be a dictionary of frequencies. So instead of going I want to pass in a frequency, I'm going to pass in a note name. So what we're going to do is do note name. Now notes, there are 12 notes in an octave. Yes, I know there's only 8 notes, but there's actually 12. All the notes, if you divide it by 12, then each of these are exactly 1/12 apart. And those notes are C, we're going to start in C, because I know the frequency of C, C sharp, D, don't ask, I know there's notes in between these, and there's like a D flat, but it makes the maths really hard. D sharp, an E, an F, have I got this wrong by the way, an F sharp, a G sharp, an A, and then an A sharp followed by a B. Those are the notes on a piano. Ooh. There we go. So what we're going to do is bass equals 262, because that's my bass frequency of my first C. And realize here I've not got an octave. I've not got multiple octaves here. I've only got 1 octave, which means my song is actually going to come out wrong, and I'll deal with that probably tomorrow. Right, notes equals this. Notes equals that. For I in range. I have to use a range here. Len of note name. There seems to be a lot of brackets there. I guess I'll leave brackets out. Length of the note name. Frequency equals the base frequency times, now just trust me this, the pow of 2 I over 12. Now the 12 is actually the same as, I could just put 12 in there to be honest, is the number of notes I'm dividing it, the number of notes I'm dividing the octave into. It works right that the octave is basically going to double every time, which is why it's a power of 2. And basically you're dividing that up by 12 and then that's it done. So to work out the next octave, we can just multiply the first one by 2. Notes. This is the dictionary, so note name of I, the index of I. This is why I use an I, because I need to use the I there basically as a number rather than just as a name, equals the frequency that we picked. And also, I want to have a 0 note frequency, so I want a rest note equals 0, like that. Return notes. So what we can now do is we can now just do notes, generate notes, and that should give us a nice horrible error. Because I can't spell generate note, maybe? Nope. Note name, blah, 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 blah. Oh, there's no equal sign. Now, as you can see here, 262, next one is 26277, so on, and they've all got fractions of a frequency, which may or may not be correct, but that is what they are. Whew. What we're going to do now is we're also basically going to implement another couple of variables, so full beat, I'm going to make it 0.5 seconds long. A half beat is going to be full beat divided by 2 with an underscore there, and a quarter beat is going to equal the full beat divided by 2. Okay, here we go. So what we're going to now do is we're going to now implement Jingle Bells as a song. The song is going to be, this time instead of frequency, we're going to do note, like this. And we're going to do D sharp. And then the period is going to be the full beat. Okay, and we're going to basically copy that because we're going to do the B, but the B is only going to be a half beat. Now, those audio people will know this is originally going wrong because I said I've only got one octave and my octave starts on a C, which means actually it's going to use a low D rather than the D of the next. So it's going to da 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 da, but it's going to go da. It's going to sound wrong. It's going to sound wrong. Trust me, it's going to sound wrong. Although the B is going to be higher because the B is not this B below the C, but the B above the C. So it's going to go da 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 da. That's basically what it's going to do. Like that, and then this one's going to be a full beat. And then it does that twice, so we just go paste that in a second time. There's the second Jingle Bells. We have a D sharp. I believe this D sharp is actually a half beat. And then we're going to have a G, an A, and a B of half beats. A G, an A, and a B. So this, there's no comma there. That's a G. That's an A. Well, there we go. There we go. That's the song defined. No syntactic errors, which is fantastic. So, waves equals an empty array for note in song, just like we did above, but we're going to do waves.append, make wave, notes, note, note, song, note, note. It's going to get this value, so it's going to loop over for note in song, like that. I've done this wrong. No, I've done this wrong. I want this to be notes. Notes, so basically I'm going to look up in the array from here. By the way, if I didn't actually print this off. I did print it off. I've already demoed that. If I print that off, this is a dictionary here. So it's going to look up the D sharp in here and use the frequency to pass into my generate wave function. And I also want to pass in the note period, which will be 0.5, 0.2, or 0.25. Job done. Now, I also want to wave, if I also know in here there's a rest. Is there a rest? No. Note rest. Notes. There we go. There's a rest of 0. So I also want to do waves.append, make wave, notes, rest, like that. And I'm going to do a quarter beat rest in between each wave, okay? Whew. Output equals mp.concatenate waves. That's my output done. Very finally, what we're going to do, I'm going to nick this line of code from up here. Jingle bells. That I believe I'm missing a note at the end. Possibly not. But the issue here is those two octaves, because I've only got one octave. Notice I've got these frequencies. Think about a piano, we have more frequencies. It just loops and loops forever in both directions until you can't hear because it's either too low or too high. However, we're 20 minutes into the video and we have managed to get it working. This actually is basically music from literally scratch. We are generating the audio curve from scratch using NumPy into an array. We write that array out and we're controlling those frequencies as it goes through. That's basically it. That's all of music defined in one 20-minute video. We now never need to do a video on music ever again because that's it. Solved. Mathematics. Job done. I will put a link to the blog of the chap who actually is much better at explaining some of these things than I am. But yeah, we can basically use it. What's interesting about this, what I found interesting about this one, is that it actually synthesizes and makes the WAV file faster than you play it back. So we could actually use this to generate and then stream to our audio. We actually make an audio buffer. We could use it inside a Pygame or something. You could generate music on the fly rather than just playing something else. That's possible because of the speed of my computer these days. Possibly older computers won't be able to do that, but this certainly, I'm not sure that would work as effectively on a Pi, but it does on my Mac. Anyway, that's it for now. Thank you very much. Sorry this is a long video. Hopefully this makes up for yesterday's.